I have to click, got it, I think. Only on one computer, okay. Good, there he is. So I want to start with an analogy once I get my computer to work. My normal life is in Berlin. And when I first told my non-academic friends that I'm going to go do a sabbatical in Hanover at Dartmouth College, they were like, poor you, Hanover, that's sad. But you could commute, you could stay in the city and just travel this 1 hour and then come back every day and still have a good life in Berlin. But of course, the spelling is wrong, and I had to for them, I had to move in America into the picture. I'm going to do this for you as well. Some tectonic magic is going to happen here. And so that was a much longer trip, obviously, but the destination was also much more rewarding. Nothing against Hanover, obviously, like the original one. But irrespective of the distance, I want to use this for an analogy. So as we travel through the world to explore different places in the world, we're also like exploring these different locations, but we have to move from A to B. And the analogy is that much like we move through the world, our eyes move through the visual scene from one location to the next. And so they really are what I think of as the Marco Polo of the human body, and to see different aspects of what's in front of you. So much like I traveled across this map, your eyes are traveling across this map or other parts of the scene right now. And I recorded my own eye movements on this. And here's a recording of that, where you see that the eyes move really quickly to different parts of the scene. This is real time. And you see the sequences of really rapid saccadic eye movements and fixations in between these little blobs at different locations. And we do that because we best see where we're currently looking in the fovea. So if you fixate Berlin, you see the details of the light in the map at that location. You make a movement to the next location, maybe, I don't know, Frankfurt, whatever. And you get the same benefit there. And so we got the terms out there. So vision is a very active process, taking in all that information 3 times a second, everything changes on the retina. And the saccades really define the input to the visual system in that vein. Now, that's, we know that, but still the research in this domain is largely separated between people who study vision and people who study motor control. And that's reflected in different departmental structures, conferences, and journals that treat motor control or treat perception, but with little overlap. Influential theories in perception that separate perception and movement control, or also assume that there are separate visual systems for perception and action. And most investigators in this field really ignore the fact that there's movement while people are perceiving. And finally, even the people like myself that study the interaction between motor control and vision, we often treat movements as something that is a nuisance to the visual system that needs to be suppressed. And so you have saccadic suppression, or also in other domains, sensory attenuation for touch when you tickle yourself, or self-produced language. I should breathe. Yeah, so I think these are really symptoms of a field that considers perception and motor control as fundamentally separable, and that can be studied in isolation. And I don't share that. In my lab, we study this as a conglomerate. We study perception in the face of movements and cognition in the face of movements, and try to see if they interact or coalesce in some ways. And in today's talk, I'm actually going to talk about the impact of movements on sensory processing. I'm going to tell you about a taxonomy that we came up with to make distinctions between different types of sensory consequences. And we'll then focus on 3 different projects in the lab that show different aspects of this interaction. One is foveal prediction, one is intrasaccadic vision and how that could be useful, and one is traces of action in the perceptual system. for now, this all sounds very abstract, but it will hopefully become more concrete. All right. So I want to start with the taxonomy. I came up with this last year, so this is up for debate, obviously. But I like to now distinguish sensory consequences into 3 different classes: intended, intrinsic, and incidental. And I want to illustrate that with that scene here of my daughter looking at flowers. So when you are in a natural situation, several things happen at the same time. She's interested in these flowers. She will move the flowers closer to her to have a closer look at what's going on, like what's there to be seen, to be discovered for her. She's going to move her body and her head closer to the flowers to have the same kind of benefit. And we would call these intended sensory consequences, right? We move because we want to change the sensory input. At the same time, internally in the brain, there are things going on. Like as you prepare a movement from one flower to the next, or as she does that, she's actually going to shift attention to that target before the eyes arrive at that location. We call that a pre-saccadic attention shift. You become better at seeing the details of that flower, even though you're not looking at it yet. So these are intrinsic consequences that happen internally in the brain. And then finally, there's something we call incidental consequences. To move the fovea from one location to the next, you actually have to shift the entire sensory surface across to a new location, which will generate a strong motion input, which is not the desired consequence of that movement. The desired consequence is to look at that flower. But it happens, and it has to happen because you're dragging your retina through the room. So we call that incidental because it's a side effect of what you actually wanted to do. And to come back to this example here, as you move the eyes over this map, you can have a look at what happens at the retinal image. This is just the part, the foveal part. But as the eyes move, the image on the retina shifts all the time. This is slowed down by a factor of 2 and kind of creates this input to the visual system that has all these motion phases in between the fixations. So we have, intrinsic consequences, planning a movement from some place to Berlin, for instance, then the incidental movement consequences in the middle as you saccade, these motion streaks that you see here. And then you arrive and you have the intended consequence of looking at that new location. There's a lot going on in the chat. I don't know if anyone's monitoring that. Okay, good. That was probably just a microphone then. Okay. Yeah, so I want to focus on a few different projects that we've done recently to kind of elucidate different aspects of this. We work on very many topics in this domain, and this kind of helped us shaping our thoughts about it. And the first project is about intrinsic consequences and about foveal prediction. And this is work by Lisa Kröll, who you see on the next slide. But I want to come back to this analogy here. So as I prepare to move to Hanover, obviously the analogy would be my pre-saccadic attention, my pre-move attention is in Hanover. I'm trying to figure things out, how things work here, and I prepare myself to arrive at that location. I know if I need to bring a guitar, if I need to bring my coffee machine, if these things are available here, things like that, right? So I can prepare myself before I go to that location. And in that analogy, I am the fovea, and I'm going to arrive at that new location. Can we show something like that in the lab? That the fovea prepares for the next thing to be looking at, that we'll be looking at. And Lisa, so she's a phenomenal graduate student. She was going to finish this year later. She did some really exciting work. I find you judge yourself, but I really love this. She had people looking at the center of the screen to answer this question. And people did that. And then there was a noise background, as you see here. It's 1/f noise, and it was dynamic. It changed every 25 milliseconds. And then at some point, a target would appear, which is really just a part of that noise, but it's filtered for orientation. And that kind of told people to make a saccade as quickly as possible to that location. And then they would do that. Now, while they were preparing to make that movement, seltzer water, sorry. There's about a 200 millisecond opportunity, a time window, when they are not executing the movement yet, they're planning it. And in that time window, she would show these other filtered gradings that would appear in the fovea. And they could either be like this one. Well, we'll talk about that later. And then people had to execute the eye movement and report the orientation of that foveal thing. They would execute that, and then what did you see as stimulus at the screen center is the first question. And then if it was there and if you saw it, you would have to answer the question, what orientation was it? The question now is whether the fact that you're going to be looking at an oriented grading in the future is affecting your current foveal perception. And so this is one over F noise, as I said, and it's a dynamic stream every 25 milliseconds or 50 milliseconds, I should say. This changes the background. The target appears and at 10 degrees eccentricity, and it can have one of two orientations and appear on both sides of the screen. And the probe could either be absent on 50% of the trials or present. And when it was present, it could either be incongruent with the target or congruent with the target. And that's going to be important, because what we want to know is if people are better at seeing the congruent information than the incongruent information, even though the orientation of the target never plays a role in this task. Okay, right. So then, there's only the target left. This is only for 50 milliseconds that you see this foveal probe, and it's embedded in dynamic noise. It's really hard to see. And then you execute the saccade. I give you an impression here. So this is a kind of an animated version of this, where I think I have a pointer here. So saccade target is here. You see that? And then the foveal probe sometimes appears here. It's in this case incongruent. Yeah, does everyone see that? So you do this trial by trial, 7 sessions, 1.5 hours each, lots of data. So much fun to be a subject in my lab. And so here's a congruent version with the probe in the fovea actually adjusted to the contrast threshold of a person. So it's even harder than that. But it works, and you see the data. It's quite nice. So here's the data. It's the first analysis. The first thing we did is look at people's ability to detect that probe in the fovea, and as a function of whether that probe, when that probe was presented, and whether it was congruent with the target or not. Generally, people are. Do you see my mouse? You do not. Can I change that? Maybe I can't. Hi, this is good. So generally, people are about 70% correct in this task, like a long time before the movement starts. What's happening here on the x-axis is the time before movement onset, so before you actually execute that saccade, and then up to 250 milliseconds or longer. And this is hit rates. How often do they see the target when it was actually presented? And they're 70% correct, then it goes up to 85%, and then it generally goes down. Okay, as you shift attention to the target of the movement, you become worse in the fovea. But on top of that, you see this difference between congruent and incongruent, which is not there initially, but it develops over time and shows up about 200 milliseconds before the saccade is executed, where you see that congruent information is detected more easily than incongruent information. This is a difference plot over here. Now, this is a scenario where you have noise on the screen all the time. And so there's not like a situation where you have nothing on the screen. And so we actually predicted that in the case of absent trials, you would also see that. You would become sensitive to information in the noise and report that information more often than when there is no congruent information. And that's that difference here in false alarm rate. So these are false alarms. Now, if you're a signal detection person, you're like, this looks like a bias or something. You have more false alarms, but also more hits. So the beauty of noise is that you can analyze it and do a reverse correlation and actually see whether those false alarms are based on signal or just really a bias. And so what we did is to filter the noise in that central portion of the screen and filter it for different orientations and different spatial frequencies, and find out for each noise patch during each time window and each trial, how strong was the energy for a certain orientation and spatial frequency. And you can then plot those filter responses and normalize them, and then average them for all the trials where people reported a congruent false alarm versus an incongruent false alarm. And that's what we did. And what you see here is, again, like a complex graph where the orientation of the target is here at 45 degrees, everything's been rotated that way. And so this would be the congruent orientation. Incongruent would be the opposite side. And you see that for congruent false alarms, there's a lot of energy in this map. So, across different spatial frequencies for target congruent orientation. So a lot of noise that gave rise to congruent false alarms actually contained information that was similar to the target. And in the other case, in the case of incongruent false alarms, you had an absence of that information and the presence of incongruent information at the same time, which suggests to us that it's really becoming more sensitive to the features of the target stimulus rather than just reporting the target stimulus irrespective of what's happening in the noise. The other thing we wanted to know is whether that's foveal, right? Is it really like a foveal effect, or is it something like feature-based attention that affects all the different locations in the visual field? And so what we've done is, I think we tested 39 different locations along this axis around the fovea. There was a longer experiment than the previous one. No, we didn't do the noise analysis, so I think we're good. But we saw that congruency effect again. We replicated that in the fovea, and then it drops off. The difference between these two curves, it's now like congruent versus incongruent, drops off towards the sides. Of course, also performance drops off, so this could be like a gain effect. But we actually did another experiment then where we just tested this location or that location and lifted performance up to foveal performance and did no longer see that congruency effect. So it's really a foveal effect. That's what we concluded from that. So one of the things that happen as you're making a saccade is you shift attention to the target. That information is somehow influencing how you prepare for that target in the fovea. And we call that an intrinsic consequence of an action, in this case, a saccade. Good. Part 3. I want to shift gears and go towards a different thing, incidental consequences, these rapid motions that happen as you execute an eye movement, and that happen across the entire visual field. And to remind you, that was here. You make saccades, and you have this shift of the image on the retina all the time. When you replay it like that, you actually don't really perceive it also. So you kind of have to stop the movie and look at the motion streaks, given a certain integration time and so on, to really appreciate what's going on. And that's kind of what we did here. This is a simulation of integration information in the retina as you make an eye movement, resulting in these strong motion streaks. And we never perceive that motion. And that's been puzzling people since Helmholtz, or even, I guess, Alhazen, or some really long ago researchers that were interested in this question: why do we not see motion during saccades? Or we were talking earlier this week, why do we not see our own eye movements in the mirror, and so on, right? And so an abundance of work has been published on this question, and people have been super creative in coming up with ideas of how that could be solved. A lot of them were extraretinal mechanisms. That's also something that people teach a lot, I suppose, in the textbooks. that you have some kind of a suppression of the visual signal when you execute a saccade. The brain knows there's going to be a saccade. The motor cortex can tell LGN, for instance, to shut down the gain during the saccade. So that's one idea. There's retinal mechanisms that are based on shearing forces that photoreceptors bend during the saccade and become less sensitive. And that's why you have less sensitivity to contrast. There are some ideas from mice experiments that global motion influences ganglion cell properties that makes them less sensitive to global motion. There's some work on metacontrast masking, smearing, and masking by structure. There are some higher level mechanisms. All of these are targeted at trying to find out why we do not see motion during saccades. And yeah, I feel like that's asking the wrong question. I feel like, I mean, it's an interesting question. And we have numerous accounts now, and they probably all play a role. But we've reviewed this to basically make the point, why doesn't anyone ask if that motion is still useful? Maybe it's still used to some extent without becoming conscious and has functions in the visual system. And that's something we've pursued. So here's a different picture that I also like to use sometimes. And you see a sequences of 4 fixations and 3 intermediate saccades. And you can look at an object in that picture, like the bear cub here in the middle. And I've shown you earlier that the scene moves across the retina as you move the eyes. And what that means is that every object like that bear cub is going to shift places with every eye movement. So for the first fixation, it's going to be there, 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 and then there, okay? And so somehow the visual system has to keep track of these objects. And some of my prior work that also Viola mentioned has focused on attentional mechanisms that support this continuity. Here we were asking the question if these intermediate motion streaks might actually help establishing continuity as well. And this is work by Richard Schweitzer, who was a phenomenal graduate student, now he's a phenomenal postdoc. It's incredible, like these people are, I don't know how they do it. Anyway, so he had this paradigm where he had people fixating on the center. I think I can still use the mouse here to help people online. And then there were like 6 objects popping up on the screen. And one of them loomed briefly, that became bigger. And that was kind of the target, the definition of the target that you had to move your eyes towards. And the trick was to have people execute that movement, but during the movement itself, we rotated the display so that the target would actually move to a new location really quickly within 14.6 milliseconds, very continuously, I should say. And then people would land in nowhere and execute a corrective saccade. These corrective saccades happen automatically. You can make them because you're not on the target. You look for the target and you go there. And the question was whether we can find evidence that if there is continuous information about the position of that target during the saccade, whether that helps you making that corrective saccade. And compare that to a situation where this is just jumping you to a new location and not giving you this continuous information. Now, 14.6 milliseconds is not a lot of time. So we use this really high-speed projector that I also have now here, like the company lent it to me for the time I'm here. So if anyone has ideas, there's one in the building. And so 14.6 milliseconds on this system means 21 frames. You can actually continuously move the stimulus to its new location. We also manipulated for how long the visual information about these targets, you see that they differ in their polarity, how long that is available for either 0 milliseconds after you land or up to 600 milliseconds. And wanted to know like how much does this surface information contribute to the corrective saccade, how much does the internal streak or the intrasaccadic streak contribute to the saccade. Okay, and here's the data. What do I need you to look at? So we have time on the x-axis, and that's not, there is also time relative to saccade offset. So you land, how much time later did the mask appear to cover up the sensory information about the stimulus. So this was the 600 millisecond condition, this is 0. And here is the performance in this task. How often did a corrective saccade happen to go to the target relative to the opposite location? And in the case of a streak that is not present, that's the purple line, versus present, that's the green line. Or actually the green data points, I should say, the lines are just fixed. And what you see is the difference between these two conditions, and it's significant in particular when you do not have surface information after the saccade. But it actually, there's no interaction with time that's statistically significant, but we think it's mostly related to a shift of the availability of that information to an earlier time point. So when you fit this, we can actually see that the system starts accumulating evidence about the target location earlier when there's a streak available than when there's no streak available. So this function shifts to the left, basically, by pretty much 14.6 milliseconds, which is the duration of the streak. Yeah. So again, we used noise patches. So that gives us an advantage. We can again do something like reverse correlation and ask, okay, this is a relatively small effect, but maybe it's a mixture of different things. And you can imagine that if you make a horizontal saccade, like in this case here, and you have a vertical stimulus, this is not a noise patch, obviously, but this is a pure vertical stimulus, that stimulus will average out over the saccade because there's white and black components of it as you move across it. But if it's horizontal, it will actually leave a trace, a motion streak. And then there's something in between, right? So we can analyze again, like the noise patch and the content of the noise patch for these different orientations. This time it's a little more tricky because we also have to take into account the motion trajectory on the retina and how that thing travels across the retina. So we want to know the angle of that path and correct the orientation relative to that. We do that and then go back and have how well does a certain patch of a certain orientation and a certain spatial frequency predict the corrective saccade going to the target. And you get maps like this, like low spatial frequency information, this is like coarse information, basically helps you always because it's always generating a streak. Orange means a lot of the saccades go in that direction. But that is even the case like when you have an absent stimulus and there's a break in the trajectory. If you have a present stimulus and it's continuously moving, you have an additional benefit. And if you look at the difference, you see that if the saccade target direction, which is here this arrow, matches the orientation of the stimulus, which is this little line, then you have most of the benefit. We also looked at latency of these saccades, how quickly you execute them. And that's plotted here, very similar analysis. And in the present case, actually in the absent case, we didn't find much here. But if you take the difference between present and absent, you see that you make faster corrective saccades when the stimulus shifts across the retina in a way that's parallel to its orientation. So motion streaks, when they are generated, actually help you making a quick corrective saccade. So here's an example of a natural scene. You go from fixation 1 to fixation 2. And as you execute that movement, you have this motion streak. And that literally gives you spatial temporal continuity on the retina of where these things are and might be used by the visual system to detect them. And with corrective saccades, I think we've made a kind of an implicit case for that. We've also done experiments where we actually ask people, where did this thing go? And we find the same effect. But that's less exciting. Okay, how much time do I have? I think I have time. Good, so incidental consequences. So this happens all the time, 3 times per second throughout your lives, more than 100,000 times a day, right? You have these experiences that you don't experience. So it must somehow have an impact on how your visual system is set up and how it computes things. It must be set up in a way that it expects these things 3 times a second. And, is kind of shaped by that information. And in a recent opinion paper, we described how we think it might actually affect visual processing. So if it does that, we were thinking, if saccades generate this input all the time, then maybe we can find traces of saccades even when people are fixating, like traces in perception that link perception to the movements that the perceptual system normally observes. And for that, we can use something very reliable in the oculomotor system, which is a kinematic law that connects the amplitude of a movement to its speed and to its duration. And that's called the main sequence. And you see here kind of a plot of that. This is when you displace a target by different amounts of angle. You have people saccade to that new location and record how fast that movement was, peak velocity. Or you record how long that movement was, the duration. And the 3 are kind of a triangle of generating the same thing. And so if you do that in a certain subject, that subject will show this dependence of peak velocity on displacement. Another subject might show like a different magnitude of this, but the law is always the same. There's always like this log linear function that connects the 2 things. So we were interested in the visual consequences of that. If you think about a small saccade, it displaces the image by a small amount and at a relatively low speed. If you move up that that main sequence, you will have larger movements that generate larger motion with like larger amplitudes with higher velocities. Now, this means that we can simulate a motion across the screen that follows this law and see what it does to perception. And we will actually simulate object motion that follows these functions and then compare or like measure the object velocity threshold where you can still see the movement and then compare that to the main sequence. So this was probably completely unclear, but I will highlight this with a paradigm. So here you see the paradigm that I used. This is actually my project. This is why it takes so long to write up. And I hope that I can write it up here. So we'll see. People are fixating in the center of the screen. We like that in the beginning. And then in this task, nothing else will happen with the eye movement. So they will just stay there in the center of the screen. But there's a Gabor patch appearing on one side of the screen, and it moves to the other side in a circular, like not circular, but like in a curved fashion. And then people had to say, did it move slightly above or below, like the upward curvature or downward curvature? That was the task, the 2 alternative force choice. And again, we ran this in a number of people for several sessions so that we had 4,000 trials per person, and then excluded just the trials that had blinks and so on. Now, again, we used this high-speed projector because we wanted to reach speeds with that thing that were basically at the speed of a saccade and still have smooth motion. And it's really fascinating. I can show you upstairs when you have time and drop by. You can do a demo session. If you have a slow movement like this one, it's easy to judge. You see the continuous motion, obviously. You go faster. At some point, when you hit a certain speed, it will not be distinguishable from apparent motion. It will look like this. Okay. Even though if you take a slow motion camera and point it at the thing, you see it's actually moving, but perceptually it's gone. Now, what is that threshold? What gives you, like, lets you go from seeing motion to not motion? And so we manipulated this for different amplitudes and also different velocity for each amplitude, which were actually scaled by the expected velocity of a saccade. So 1 here in this relative velocity variable is the speed of a saccade of that amplitude. And this would be slower and this would be faster. And so you see that they will have different durations depending on the peak velocity of that movement. Now you remember each of these amplitudes will have a different peak velocity, but we will express it in terms of the relative velocity to a saccade, okay? So we will scale it, but only in the second step. So here's the data from that experiment. Here's absolute velocity on the x-axis and proportion correct in this task. How often can you say upwards versus downwards curvature? And you see that here's the movement amplitude in different colors. Dark is large movements, bright is small movements. You see that velocity threshold, or I guess the smaller the movement, I wanted to say, the slower the stimulus has to be in order to be seen. That's basically this curve here. If you have a very large movement, you can move it at a higher speed and still see it. And this is moving not at this is actually moving at a constant speed in this experiment. Now you can have predictions. So if you had a threshold that would basically depend just on the velocity of that stimulus, you would have a flat line here, which are these dashed lines. And if you would have the threshold depends on the main sequence, on the relationship between the amplitude of that movement and its velocity, then these solid lines would be the prediction. And if you take the threshold throughout the data up there, you actually see that it follows the prediction of the main sequence. You can normalize the speed, as I did before, for the expected peak velocity of a saccade of a person. And then you would have the opposite prediction. Now you have the flat line for the prediction that it follows the main sequence, and you have these other predictions in dashed lines that would fall off with the function of amplitude. So really the moment when you stop perceiving this thing as moving relates to the main sequence, which is a kinematic law of movement, like motor movement, not perceptual movement. You can do the same for duration, like the duration of that movement rather than velocity. And again, it's not based on that. It's not like you have more integration time, and so you kind of have a better chance when you have a larger movement. If you normalize for the movement duration of a saccade of the given amplitude, again, all of these curves fall on top of each other, like perfectly. And these are the predictions again, which nicely follow the same scheme. I was blown away by this when I first found it 6 years ago. That's how long it takes a faculty person to write a paper. But we did so much more since then, so I guess I have excuses. One thing that we did is to look at, to replicate this, but manipulate for how long this stimulus was actually seen in the beginning and in the end of the movement. And previously, we had this on for 200 milliseconds, then it would move to the new location and then stay on the screen for another 200 milliseconds. And this is a new experiment now with different people. Again, like almost 60,000 trials. And you see we perfectly replicate that finding. But you see, there's the other extreme where you just see the motion and not the stationary points in the end and in the beginning. And we wanted to know, do you need those in order to have that effect? And indeed, when you do that and don't have a stationary target in the beginning and the end, just the movement, you see exactly the opposite pattern. You see that perception is just a function of the absolute velocity rather than the main sequence. So the question was, how much time do you need to kind of look at these two targets and generate amplitude information about that stimulus, basically? And the answer is almost nothing. So we had the shortest condition at 13 milliseconds, and that was basically sufficient to recreate the finding that we had initially with 200 milliseconds. So just a bit of information about where this thing started and where it ended would give you back the same results, that your perception depends on the combination of amplitude and speed. Right, so to assume the main sequence relation, the stimulus needs to have movement, start, and end points. So it could be some form of meta-contrast masking that is contingent on saccade-like kinematics of the masked motion. And we actually did try an explanation of that. I think I'm good on time, so I can try that real quick, or can I? Yeah, it's 4 slides. Where we simulated what happens in early vision when you present these stimuli, very simple model, and see whether it makes predictions that we can use to compare them to the data. So we took the paradigm and put it into a model where every location on the retina was basically simulated with a certain spatial profile, very narrow spatial profile. So this could even be retinal or like V1, like very small receptive fields, you could say. And a certain temporal response profile. So this, normally when you show stimulus, you will have a neuron fire for a certain time. And when you do that with a stimulus, you get maps of this kind, where this would be a 4-degree movement from -2 to 2. And you have activity in this map. This is the X position and the Y position. Y has the curvature, X has a main motion. And you see this here for a quarter of a saccadic eye movement speed or full saccadic speed. Now, these, you already see like that there's much more information during the movement in this case than there is here. But we normalize this the way that people do this. Naka-Rushton functions kind of assume that there's a saturation of the neural response. And so we kind of at every time point went through this normalization and computed the difference between there being a continuous motion and there being no continuous motion in that location. And that's that difference here. So if there is continuous motion, this would be this black condition, static plus moving. So you have the static objects in the beginning and the end, and movement in between. Or you just have the static objects in the beginning and the end, and no movement in between. So that's that difference here. And if you go to higher velocities, that difference is much smaller. Now you can probability summate over that. That's what we've done to see how much evidence there is for a certain presence of motion or not. And of course, with increasing velocity, this is this velocity factor, there's going to be much less evidence over time, like for that there is motion present. I'm starting to stutter now. I don't know why. So you can have some arbitrary threshold. We put this here at 2.5, but it really doesn't depend on that much, as you will see. And then generate a psychometric function, have a random process that uses that evidence to determine whether a stimulus was present or not. There's some noise in the data because we implemented fixation on eye movements during the fixation, and we also added some noise that is amplitude dependent. And so then you get a psychometric function for the model output. And we can compare that, this is the 200 millisecond condition, to the actual data. So this is for different masking durations or like presence of that stimulus in the beginning and the end. And you already see that the model output reproduces this finding of shifting the function when you have a smaller amplitude of the movement or a larger amplitude of the movement. And that's because that evidence goes down more slowly in the presence of small movements as compared to long movements. And as soon as you have these masks, all of these different functions at different movement amplitudes, which you see down here, they fall on top of each other. And so there's no longer a distinction between them in the psychometric output. So it's a very simple mechanism that, you know, assumes nothing new about the visual system. It's actually a much simpler visual system, maybe a frog system or something like that. And you can compare this to the data, and it's very, you know, qualitatively similar, even quantitatively, I would say, even though we didn't really try to fit this to the data. Yeah, and that's my summary slide, I think. So I showed you, well, first I introduced this taxonomy of different sensory consequences of movements. And we usually think, when we think about movements in the service of perception, we think about their goals and their goal-directed consequences. And I've highlighted that there's also intrinsic consequences that happen internal to the brain, and lots of these are linked to attention and predictive processes. And there was one example that I gave of phobia prediction. You become more sensitive to things that you're soon going to be looking at in the phobia. And then there's incidental consequences, these side effects of making a movement. And we have done some studies trying to see if they have functional consequences for the visual system and not just, you know, suppressed or attenuated because they're a nuisance. And we find some evidence that they provide continuity of objects across eye movements. And then finally, I said that incidental sensory consequences may shape perceptual processes to an extent that you could even find traces of them during fixation. And that was that experiment with motion detection that I just talked about, where we had a model of early visual processing that reproduces this relationship that we observed in that data. Yeah, and so I want everyone to think more about how vision works in the presence of movement. And I got a whole team of people doing that in my lab. And I want to thank you for paying attention to this. And I'm happy to take questions. Thank you.
About 10 minutes for questions, and just for the Zoom people, you already on, they have to, I think the audio doesn't work, so they can just write in their questions.
Yeah, I will take care of the chat and then interrupt you.
Or maybe you can take care of the room, or do you take care of the room? Do I take care of the room?
You can take care of the room.
Okay, I can take care of the room. Okay, any questions? Yeah.
Yeah, really beautiful work. So my question is about the first set of experiments of the pre-saccadic modulation of orientation perception. And it sounded like your interpretation was something like once you have some information about what the target orientation is, that causes some change in the perception of like the current location. But I wondered about an alternative interpretation where if there are somehow spontaneous fluctuations in sensitivity that makes you more likely to detect the target. And so it's actually the other way around, that you are more sensitive to a certain orientation in a way that just makes it more likely that that data is eligible for that trial because you're making the saccade to the target correctly.
That's a really interesting hypothesis. I don't think the data fully supports this. So I think that the point that would speak against it maybe is you would if that were the case, you would expect the effect to be biggest in the beginning, right? When you first detect the target and you prepare the motion. Yeah. And then it should like maybe become smaller. And I think maybe, I don't know. I mean, I don't know exactly the time course of this, but you would have some sensitivity to the target orientation before you even see the target. And that would be reflected, I guess, in the data. But I think, so that's not the case, like long before the saccade. Would that be a good argument?
Yeah,
yeah,
I think so.
Okay.
Yeah,
it's already impressive.
When I no longer have this plot.
Yeah.
So yeah.
Yeah, no, yeah, it's a very interesting thought, actually. That could be the case.
Yeah. Okay, great.
Yeah, other questions?
I have a quick question since we're on this slide. So that you get that improvement in performance relative to baseline. Is that performance improved because people know that there's no critical stimulus appearing in the phobia? Is that what accounts for that 15% boost?
Yeah, there's a lot that, I mean, you mean this difference here, right?
Yeah.
That's a big effect. I don't know exactly where it comes from. I think it has to do with like first monitoring the periphery for the target to appear at some point. This is when you're still bad at that phobia location. Now you've detected the target, you can execute the eye movement and also do the perceptual task in the phobia to a greater extent, I suppose. I don't know. I feel like most of the time in these experiments, when we do saccades and probe at the same time, you're much better off not trying to solve the perceptual task in the first place, but just do the eye movement and then let the visual system do the rest. Which is why my argument just now, I didn't really buy it myself, but yeah, I think that's what's happening. There's something about the task that needs you to do one thing first, which is detect a target, then prepare a movement while detecting the probe. That might account for the difference. It becomes successively more difficult as you approach the movement itself, because that's where the drop is there, because you're shifting attention to the saccade target. Yeah.
I have a question about this slide as well.
I should put up the random slide and people have
you present two kinds of false alarms, and a false alarm is a response that is I saw something at the phobia when there was nothing there. And these two kinds of false alarms are either more congruent with the target or more incongruent with the target based on what noise there was, right?
No. So in this case, yes, I mean, that is the next slide finding. But why we have 2 lines here is because we asked 2 questions. Was there something in the phobia? And if there was, we asked them what orientation was it. And so if they had a false alarm, they told us which orientation they saw. And we didn't ask about congruency, the subjects, right? We never told them that this is the question. But we plotted as congruent to the target versus incongruent to the target. This is where the 2 lines come from.
That makes more sense.
And it doesn't depend on time because we don't know when they had this hallucination of a false alarm, right? So we cannot resolve this, which is why this is just 2 flat lines. That's just because you would have to tell them. Yeah.
Just a quick clarification question still on this slide. And then we'll flip to another slide. But so there is no task on the target, right?
No.
Just to make the saccade.
Mhm.
And so I guess that's the difference between what I typically do in life. Right? I typically make a saccade to potentially engage with something I'm about to look at. It's
Mhm.
rare that I'm going to expect to do a task in the location that I have
Mhm.
just left.
I agree.
And,
Well-
and so sort of thinking about the extrapolation of the take home here to my normal, saccadic life, do you think that this effect would still happen if rather than 50% of the trials,
Mhm.
I'm forced to do a task at fixation, say it's extremely rare, 5% of the trials, I'll sometimes be given this surprising question about what might have been happening at fixation, or maybe the effect is really caused by the sort of working memory, focus on the phobia. That's a little atypical.
Mhm. Yeah, it's a good question. I mean, we made this by design to make the target as irrelevant as possible. So we didn't want that to be important to the task,
Yeah.
other than just make this account there. But the phobia that becomes important just before you execute an eye movement. Yeah, that's something that is kind of maybe unusual. We don't really know what the phobia does in natural situations. There's some literature looking at, it's 2 different processes, the target selection and the foveal computation or like processing, because you want to start programming your next saccade before you're done processing what's in the phobia. So I think there is a lot of overlap in these 2 processes, and you would probably still find it if you made it very unlikely to have a target, to have a probe in the phobia.
Mhm.
I think so. I think you would make it much more likely to find an effect if you had made the target relevant, right? So that would have been a problem. But in the reading literature, for instance, this is one of the literatures where people look a lot of foveal processing, because that's where the eyes are currently looking. And they assume that for as long as the eye is looking there, there's some processing going on. And there, people look at influences of changing the word in some way as you move to the next word. And they find these influences relatively late, so up to 17 milliseconds before you execute this card. So I think there's still processing going on. But again, in reading, you have a foveal task. I guess in natural life.
Do you think there's a congruence effect only for the phobia? I mean, why not elsewhere?
Yeah, we think so. And actually, so we did this experiment here where we probe different locations. I showed this earlier. And you find this effect only in the phobia and not somewhere else. But I agree, it could be somewhere else in principle if we would be able to establish a peripheral phobia, which is a thought that I can have, if I attend to a different location in the scene, maybe I get the similar prediction of features that will arrive in that location when you make an eye movement. It would be in the periphery, but you might have that effect. But the phobia is special if your task is, it is special. Yeah, actually, this is kind of that data, so I don't really think that's the case either. But I think it's a special place. We looked at saccadic landing sites in this thing, which makes an interesting prediction with respect to your point. If you land short of the target, you actually expect the phobia stimulus to be still not quite in the phobia, so it hasn't quite reached the phobia. And we wondered if then you become more sensitive to the phobia or the predicted location of that stimulus where it will actually land. And it's still the phobia. So it's still not the location where you know that, or your system might know that that stimulus will land because you undershoot the target. So it seems to be really something specific about the, maybe even anatomical about the foveal representation in visual cortex.
I wonder if you made them do a devil's advocate test. So boom, boom.
Mhm.
So they've got
Yeah, I've done that experiment without features. But yeah, I don't know. I would doubt it happens. And Lisa would certainly doubt. She thinks it's the phobia. It's just the phobia. My student who's working on this.
I think we will stop taking questions now. Because
Okay.
The class has 10 minutes here, so there will be a reception now. And just outside here with coffee and donuts, you can all come and talk about more. And then just a reminder for all the grads and postdocs that later on today at 5 o'clock there's a